Chapter 12, and we are looking at 12.3, which deals with exponential functions. It starts on 735. So 12.3, exponential functions. Okay? Now, why do you think this function is called? Why? Good. Why do you think this function is called? Because why do you think this function that I haven't even presented to you is called exponential? The exponent is the variable. Exactly. So this is how the exponential function looks like. And what is a? A is a constant. A is not a variable. So a is the base. However, there is a problem here, a potential problem. We cannot have the base to be 0. We cannot have the base to be 1 or a negative number. These are not allowed. And you could say, why? I can raise 0 to 4. I can raise 1 to 10. I can raise a negative number to a power. Yes, all these are possible indeed. But for the exponential function, the base cannot be, but what can it be, right? It can be only a positive number greater than 1, not 1. And it can be a positive number, but tiny, between 0 and 1. So I was saying why these are not allowed, simply because the inverse function will not exist. It's not for the exponential. It's because its inverse function will not exist. So please keep in mind, the base of an exponential function is a number that can be either greater than 1 or between 0 and 1. These are the only two possibilities. Obviously, the function will have two different shapes. When the base is greater than 1, it will have a certain look. When the base is between 0 and 1, it will look totally differently. Okay, so let's start with the first one. Say it again.
Greater than or between 0 and 1?
Yes. So this is option 1, and this is option 2. So let's look at option 1. Let's say 2 to the x. This is an exponential function. The base is 2. We want to graph it. Okay. So let's say x. Let's say f of x. And we always start by doing what or determining what when we graph a function. What is our first thought when we want to graph a function? Absolutely. Very good. Excellent. So 2 to the x. What do you think the domain of this function is? Do you think the exponential function will be friendly? In other words, all real numbers? Or it may encounter any problem? So before you say anything, let's say there are 3 types of numbers, positive, 0, and negative, right? So let's plug in a negative number. 2 to negative 2. Does it exist? It's 1 over 4, right? Yeah. Let's plug in 0. 2 raised to 0. 1. Good. So let's plug in 5. 2 to the 5th. So it turns out that this is a nice function. Friendly. The domain is all real numbers. So let's choose negative 2, negative 1, 0, 1, and 2. And let's plug them in and find the y values. Here's one option. If you want to go to the graphing calculator, and in y equals, clear anything you have, and put into caret. You know me, I like parentheses very much. So 2 raised to x, although it will work just fine if you just put 2 to the x. Let's go to second and table, and let's plug in the numbers we are interested in. Negative 2, negative 1, 0, 1 and 2. let's say 3 since I had another one in there. So the first one, -2. For -2, I get 0.25. For -1, I get 0.5. For 0, I get 1. For 1, I get 2. For 2, I get 4. And for 3, I get 8. So I put those values in my chart. And now I'm ready to graph it. From left to right, I start with -2, kind of difficult to plot 0.25. So at -2, 0.25. At -1, 0.5. At 0 is 1. At 1 is 2. At 2 is 4. And I got the idea. That's good enough. Here's a question for you. Would you say that this function is always increasing? Yes, this function is always increasing. Second thing, can anyone give us the range of this function? The domain is all real numbers. Can anyone give us the range of this function? That's it. Very good. Now another question for you. Is this function one-to-one? Yes, by the horizontal line test, the function is one-to-one. Excellent. Which means immediately what? The fact that it's one-to-one. Well, good. I want to graph the inverse. I know nothing about it, but I can graph it. So I graph y equals x first to make sure that the other one is symmetric. And I would like you to give me several ordered pairs that I should plot so I can get the inverse. Which ordered pairs will you give? Awesome. 0.25, -2. Awesome. Another one. 0.5, -1. Awesome. Excellent. And I got the idea. Here it is. This is the inverse function of 2 to the x. Great. As you notice, if the base is greater than 1, the function is increasing. Its inverse is also increasing on all its domain. Any questions? Any questions? There are two very important exponential functions. One is called common exponential function. And the other one is called natural exponential. Say it again. Yes. Yes, I'm going to present them, and we're going to look at the graphing calculator. Natural exponential function. Let me show them to you in the graphing calculator for a second. So they are so important they have their own key. See with the blue, second, and here 10 to the x? That's the common log. They're on the same key with log. A common exponential function, forgive me. So the second and 10 to the x, and the other one is right here. The natural exponential function with second, it's e to the x. So f of x equals 10 to the x is the common exponential function. and f of x equals e to the x is the natural exponential function. We're going to graph all these three because I would like you to see what happens. The higher the base, the closer to the y-axis. Okay, so we're going to graph on the same coordinate system, 2 to the x, e to the x, and 10 to the x. By the way, how much is e? Let's say we don't know. Here it is. Go to second. Go to second and the division symbol. That's your e. Second and division symbol, and press enter. So e equals 2.71828. Question: is this a number greater than 1? Okay, so they all have to have the same shape, right? 2 to the x, e to the x, and 10 to the x, they're all have to have the same shape with a base greater than 1, correct? But the higher the base, the closer to the y-axis. So I'm graphing 2 to the x now. Here's 2 to the x. Then I will graph e to the x. Definitely it passes to the same point, 0, 1. And here is 10 to the x, even closer to the y-axis. So let's do this with a graphing calculator just to see those shapes. I'm hoping that this will trigger your memory. So we have 2 to the x. Here's how I get e to the x. Second, e to the x. And here's the last one. Second, 10 to the x. Do we have this? So I have blue, I have red, and black. I go to zoom. I will use this 6, the standard viewing window. Here it comes. This is 2 to the x. Here's e to the x. In red, here it is. And here comes 10 to the x. Even closer to the y-axis. The higher the base, the closer to the y-axis. Okay? Good. So we also have the other shape, however. Yes, Becky? So let's look at the other shape where the base is a tiny number between 0 and 1. Now let's use 1/2. 1/2 raised to the x. This is the exponential function with a base less than 1. What is its domain? All exponential functions are friendly. Their domain is all real numbers. Let's plug in the same values as before. -2, -1, 0, 1, and 2. Let's go to the graphing calculator. In y equals, let's plug in that function, delete everything else, clear, we don't need anything else anymore. So in parentheses, Mike, you want to use this? Okay, so in parentheses you can put 1/2 in parentheses, or you can put parentheses 0.5, whatever you want. And the power is, of course, x. So now I go to second and table, and I already punched in all these numbers. I had them before, -2, -1, 0, 1, 2, and 3. I'm going to copy the answer in my chart. 4, 2, 1, 0.5, 0.25, and that's all I need. So let's graph. First ordered pair, -2, 4. Next one, -1, 2. Next one, 0, 1. 1, 0.5. And I got the picture. This is the graph of 1/2 raised to the x. What can you say about this function? It's definitely not increasing, but decreasing. Is it 1 to 1? Will it have an inverse? Yes, let's graph the inverse. So please give me a couple of ordered pairs that I should use to graph the inverse function of 1/2 to the x. This point where the function crosses y equals x must be a point for the other function as well. Why? Because everything that is on this line has the same x and the same y. And if you reverse 3, 3, you still have 3, 3. If you reverse 1, 1, you still have 1, 1. So I need a couple more points so I can graph the inverse. What will you tell me? Very good. Uh, 2, -1. 1, 0. That's good enough. I got the idea. This is the inverse function of 1/2 to the x. And we'll talk about it in a minute when we come back, but I'd like to look at a few problems on page 736. Yes, Becky?
Yes, here.
The previous ones?
So, this one is common and the other one is
No. This is the common, and here's the graph in green. And this is the exponential, and here's the graph in orange. And I graphed this one from before one more time.
okay.
Better? Sure. Okay, so on page 736, couple of word problems. Okay, so let's start with 41. The equation y equals 140,242 multiplied by 1.083 raised to x models the number of American college students who studied abroad each year from 2000 through 2009. So they came up with this model that represents the number of US college students who studied abroad between those 2 years. In the equation, y is the number of American students studying abroad, and x represents the number of years after 2000. So x, number of years after the year 2000. Okay. Part A, estimate the number of American students studying abroad in 2004. And part B, assuming this equation continues to be valid in the future, use the equation to predict the number of American students studying abroad in 2015. What will you tell us to do? How do I handle this? What do I have to do? X is the number of years after 2000. So then what does this represent? Very good. What does this represent? Very good. Here's what I recommend. Go back to the graphing calculator, in y equals, clear everything you have, and let's punch in 140,242 in parentheses 1.083, close the parenthesis, power, caret, and x. Don't do anything. After you put it in, go to second and table. What would you put in now? Four and 15. Very good. 4, enter, 15, enter, and we're done. If you have any doubts about this that you want to look at, here's the number. 192,926. I cannot round it up because it's a number of people, so that's fine. 192,926. And the other one, down. Can't do it like this. Okay, 463,772. Here's another application that I would like to look at. And they are based, the next two applications or so, they are based on the following formula. This will be given to you. What does, yes, R over N, and this is N, the same N. Okay, so P, principal. If we deposit money in a bank, that's the principal. If we borrow money from a bank, that's the principal as well. A, accumulated value. Accumulated value. In other words, if we deposit money, then 10 years from now, this will be the amount we have. If we borrow money, let's say 10 years from now, this is the amount we have to pay back. Okay. R is the interest, annual interest rate. T is time in years. And N is the number of times the interest is compounded or recalculated, if you want, per year. So lowercase n, number of times interest is compounded per year. It can be semi-annually, which means 2. It can be quarterly, which means 4. It can be monthly, which is 12. It can be daily, which is 365, and so on and so forth. So one more time, A is the accumulated value. P is the principal. We can deposit or withdraw or borrow. R, it has to be the annual interest rate, and it cannot be in percent. It has to be as a decimal number. N depends on the number of time interest is compounded per year. And T is time in years. It can be 5 years, 3 years, 10 years, whatever. Okay, so I'm looking at problems 47 through 50 on page 737. 47 through 50, page 737. Ready? Okay, 49. Find the total amount Janina had in a college savings account if $2,000 was invested. What is this? Which variable is $2,000 was invested? The amount was invested. Principal, of course. Thank you very much. And earned 6%. Although I cannot use 6%, which variable is 6%? R. So I will have to write 0.06. Compounded semi-annually. Which variable is that? Which means 2. n, very good. For 12 years. So which variable now? I know it's the last one, which is time, 12 years. Good. Let's just write the formula, and we have to put in the calculator. So A equals, oh, not 6, but 2,000. 1 plus 0.06 divided by 2, and the power is 2 times 12. If you don't put 24, you should put parentheses around the power. So careful with that. Okay. So 2,000. In parentheses, 1 plus 0.06 divided by 2. It's 6%, correct. Close the parenthesis. Power, in parentheses, 2 times 12. And press enter. So at the end of 12 years, she has in the account 4,065.59. Any questions? Any questions on this? Any questions? Next one. Good, so let's look at 48. Any questions here? Everyone, okay? Find the amount owed at the end of 5 years, so T equals 5 years. If $3,000 is loaned, what does that mean? Which variable is, yes, perfect. At the rate of 10%, so then 0.1 is the rate, annual interest rate. Compounded quarterly. So how much is N? How many quarters are in a year? 4. So then in this case, we have A equals 3,000. 1 plus 0.1 divided by 4. And the power is 4 times 5. N times T. With the calculator, 3,000, parentheses 1 plus 0.1 divided by 4, close the parenthesis, power, parentheses, 4 times 5. So they borrowed $3,000, and in 5 years, they have to return 4,915.85. Any questions? Any questions? Exponential function has a very wide applicability in a lot of real-life situations. A lot. It's a very nice function. It's a friendly function, really. I like it. Now let's take a look at its inverse function. 12.5. Logarithmic function. We already know its graph. We graph the logarithmic function in both cases. We graph the exponential. However, let's talk about the mechanism. So let's say I have 5, 0, and -3. These are 3 x values that I just picked. And let's say we apply the function f of x equals 2 to the x to each and every one of these numbers, of course. And I would like to determine the y value. I know what 2 to the 5th is. It's 32. What is 2 to 0? Perfect. And I know that 2 to -3 is 1/8. 2 to -3 is 1/2 to the 3rd, which is 1/8. Okay, now knowing that 2 to the x is 1 to 1, And knowing that it has an inverse function, I want to see how the inverse function works. So the inverse function will be denoted by using this, we call it operator, log. It has to have the same base right here at the bottom of the G's tail, if you want, x. So here's how we read this. Log base 2 of x. Log base 2 of x. So if this is the inverse function and I apply log base 2 to 32, what should I get back? For sure, otherwise this is not the inverse function. Exactly. When I apply log base 2 to 1, what should I get back? Otherwise this is not the right mechanism. I should get back 0. And when I apply log base 2 to 1 over 8, what should I get back? Good. In order to illustrate this, first, we have to look at the most important concept. This is by me. Okay, I consider this the most important concept in chapter 5. Yes. Thank you. 5 too, actually. No, I meant 12, of course. Thank you. Here it is. In words first. Any log equation can be replaced changed into whatever you want to say, both work fine, changed into an exponential equation, comma, and vice versa. Any log equation can be replaced or can be changed into an exponential equation and vice versa. Any exponential equation can be changed into a log equation. So you could say, why is this so important? Show me this. Well, I can't show you this if I don't show you this. So this concept will be following us throughout this chapter, this section and the next one. So any log equation can be replaced by or changed into an exponential equation and vice versa. But this is in words. So how do I translate this into mathematical symbols? So here it is. Okay. Log base a of x is a number. This is the log equation. Log equation. This is the double equivalency symbol, which means this can be changed into this, which I didn't write yet, and this can be changed into this, both directions. Double equivalency symbol. So now let's do this together so hopefully we remember this. When I change a log equation to an exponential equation, always start with the base and go counterclockwise. The base raised to y is x. The base raised to y equals x. And this is the exponential equation. Base raised to y equals x. So now I can show you the mechanism. I'm going to apply log base 2 to 32 and see what we get. So I'm on this side, log base 2 of 32. That equals y. This is equivalent to, can anyone change this into an exponential equation for us? 2 to the y equals 32. Now is the time to talk about how to solve exponential equations. This is an exponential equation. So, I see the left-hand side has base 2. I am hoping that the right-hand side can be presented with base 2. It should be, because in this class we only encountered these particular examples in which both sides can be presented with the same base. Is there another way of writing 32 with base of 2, because 2, I have the base on this side? So 2 raised to, that's it. So now we are not simplifying, we are not reducing, we are not doing anything, we are just thinking. Here's how we think. Two numbers are equal. This one equals this one. And they have the same base. What has to happen to their exponents for them to be equal? I am told they are equal. They have the same base. What has to happen to their exponents? They have to equal each other. So then y must be 5. So, coming back to our situation, it appears that we showed that log base 2 of 32 will definitely return what? 5. We're going to repeat the mechanism for 1. So, log base 2 of 1 is, I have no clue. So, let's see what that is. I want to change the log equation into an exponential equation. What do I have to write? 2 raised to y equals 1. Now all we have to do is just think. There is only one number that I raised 2 to get 1. And that number must be, excellent. So y equals 0. Let's go back. Can we definitely say that log base 2 of 1 is 0? Good. Last one. We have to show and find log base 2 of 1 over 8. Well, I don't know what this is, but I know that this is a log equation. I set it equal to y. It's a log equation, so I am interested in changing this into an exponential equation and solve that. How do I change this into an exponential equation? Equals? Good. I need to show that both sides have the same base. Otherwise, I can't conclude anything. The left-hand side, there is nothing I can do. How do I change the right-hand side? With a base of 2. I'm hoping I can't force it, but it should be there. 2 raised to blah, blah, blah is 1 over 8. That's it. 2 raised to negative 3 is 1 over 2 to the third, which is 1/8. So therefore, y must be negative 3. So we go back and we conclude that this is the case. So, of course, we have a different log function as the inverse function of any exponential. So if I say, here's the function 1/3 to the x, what would you say its inverse function would be? And remember, bases have to be the same. If bases are not the same, the mechanism is broken. It's not going to work. Yes? Yes. So it has to be log, L-O-G, it must. Now, what is the base? Of course, it has to be 1/3 of x. If you remember, we looked at two exponential functions. We looked at f of x equals e to the x, and we looked at f of x equals 10 to the x. And we said these are so important that have a dedicated key in the graphing calculator. It must be something, right? Now, what do you think their inverse functions will be? And before you say anything, look at the graphing calculator at those keys. Exactly. So f inverse for these functions, what do you think f inverse will be? For 10 to the x. Yes, however, we don't write the base. If it's log, it's base 10. It's not a mistake. If you put it, nobody will say it's a mistake. Okay? But we do not write it. So if this is the common exponential function, what do you think the name of this one is? If this is the common exponential, this is common log. Exactly. Good. So look again now for e to the x. What is the inverse function of e to the x? And yes, it's not log, but it's a very special ln. What is the base of ln? It must be the same with the base of the natural exponential function. So we know that ln, although there is no base in there, we know the base is e. Very good. So this is natural exponential. Natural log, of course. Sorry. Natural log. Very good. I would like us to practice going back and forth from an exponential to a log on page 749. We're asked to write each exponential equation as a log equation. No, write each log as an exponential. That's the first one. Okay, problem 7. Log base 9 of x is 4. They want us to change this into an exponential equation. How do I do that? Very good. 9 to the 4th equals x. We're not asked to solve. We're not asked to do anything. They are only asking us to change it into an exponential equation. Okay. Let's look at 11. Log base 7 of the square root of 7 is 1/2. Log base 7 of the square root of 7 equals 1/2. They're only asking us to change it into an exponential equation. Of course, it will make sense, right? Is this true? Of course. 7 to 1/2 is the square root of x. That's the square root of 7. Good. Let's say 16. Log base 1/4 of 16 equals -2. We want to change this into an exponential. Very good. Very good. Okay, now let's go backwards. They want us now, they are giving us the exponential equation and they want us to present the log equation. Okay. So let's say 18. I keep them in this order. The log on the left, the exponential on the right. It doesn't matter. Whatever you want to do, it's fine. But it's easier for me to explain what I'm doing. So I know the left-hand side has to look like this. A log, some base, equals some number, and a number here. I have to start with the base. What is the base? Awesome. What is this number out here? 3. And what is this number? That's it. Not that difficult if you keep it in order, I think. Okay, let's look at another. Let's say 26. 3 raised, oops, I didn't mean to write it over there. 3 raised to a negative 4 equals 1 over 81. We want to change this into an, yes, thank you. Yes, it's log base 2 of x. I'm kind of exaggerating it, but it has to be log, yeah. So when I change the exponential equation into a log equation, try to keep it in the appropriate order so you don't make a mistake. I have log, I have to have a base, I have to have a number here, and I have to have a number here. Always start with the base. What is the base?
3.
What do I raise it to?
1 over 81.
Negative 4, right? 3
Oh,
raised to negative.
awesome.
Yes, you're already ahead of me. I know. Awesome. Okay. Find the value of each log expression. Okay, so a different type of problem. Same idea, of course. Problem 31. Log base 3 of 1 over 9. I have no clue what this is. I'm going to call it y. And then I'm going to say, okay, I'm going to change this into an exponential equation that I hope to be able to solve. So how do I write this?
Raised to y equals
3 raised to y equals 1 over 9. This is an exponential equation. I need both sides in this class. There are other options. I can have the equation 3 raised to y equals 2. But we don't know how to solve this, and we will not learn in this class. So for now in this class, both sides have to have the same base. Otherwise, we can't solve. So can I write the right-hand side with the same base? Yes, 3 raised to negative 2. So therefore, this answer is y must be, the only option is negative 2. Very good. Let's look at, yeah, 40. Log base, common log of 1 over 10. They're asking us to find this. I have no idea what it is. When I see log, which base do, although it's nothing in there, which base is that? 10. So then 10 raised to y equals 1 over 10. I have to have the same base on both sides. So 10 to y equals 10 raised to negative 1. So therefore, y must be negative 1. Very good. Let's solve other equations here. Like, for example, 55. Log base 8 of x equals 1/3. Good. Equals? Good. But I know what a to 1/3 represents from chapter 10. It's the, exactly, the cube root of 8 equals x. Awesome. So therefore, x equals, exactly. X equals 2. The cube root of 8 is 2. Awesome. Okay. 61. Log base x of 100 equals 2. Log base x of 100 is 2. How do I solve this? Yes. Awesome. What type of equation is this? Right. I have 4 methods. Which is the easiest method here? Exactly. Awesome. And because it's quadratic, how many solutions will it have? Right. So what am I going to write right here in front of it? Right. However, not so fast. X is a base. What did we say about the base? It cannot be negative. It can be between 0 and 1 or greater than 1. Not 0, not 1, and not negative. And I will say, this is good. You don't have to erase it. This is the correct way to write it. And I'll say only x equals 10. The base cannot be negative. I show my professor that I know that when I take the square root, I have to get 2 solutions. But then I have to look here and say, uh-oh, no, not possible. Okay? So this is the correct answer. Awesome. Okay, so let's say 59. Log base 3/4 of x equals 3. So what do we have? So 3/4 raised to the equals x. I have to raise 3 to the third and 4 to the third. So then I get x equals?
27.
Very good, excellent. Okay, let's look at 68. If we got the picture, we can move on to something else. Log base x of 2 equals negative 1/3. I'd like to go back to more exponential equations, actually. After we finish the logs. So this is equivalent to? Good. So what does this really mean? First of all, it has a negative exponent, so it's definitely 1 over x to 1/3. Well, what does x to 1/3? We just had a similar example. What does x to 1/3 mean? Right. So I have 1 over the cube root of x equals, and here's my hint for you, 2 over 1. What is this? Proportion. Right? Let's cross multiply. One side is 1. The other side is 2 times the cube root of x. I wish I could raise both sides to, but I need to clean it up first. How do I clean it up? So the cube root of x equals 1/2. Now I'm ready to cube both sides. Okay, I cube both sides. Radical equations from chapter 10. And then x equals, awesome, 1/8. And you can say, wait a minute, you have to go back and check because you raised both sides to the third power. True, but it's power 3 and it will work. So you can go back and replace in here 1/8 and 1/8. We can do this quickly with a graphing calculator. We will get to. So here's how I do it. So in parentheses, 1 divided by 8, and the power in parentheses, -1/3. When I hit enter, I have to get 2. Okay? So it's mandatory to check, but if you remember, we said if the power is odd, the answer will be there. Okay, the same thing, nothing new in 12.7, just more equations. 12.7 exponential log equations and problem solving. Okay. So in the first set, it's asking us to plug in a number in the calculator, like number 5 on page 762. And this is the end of what we have to do. We're asked to find this. And in problem 9 on the same page, we're asked to find this. So all we have to do is just plug it in. So let's plug in natural log 2. Close the parenthesis and press enter. Got 0.6931. For log 12.6, log 12.6. 1.1. Then we're asked to find the exact value. Let me copy a couple of problems, like 23. Log 10 to the third, and please tell me what you get. And 25, natural log e to -7. And let's say 29. Natural log of the square root of e. How much did we get for the first one? Yes. How much do we get for the next one? Correct. And for the last one? It's correct. It's 0.5 or 1/2. Okay, let's take a look at 41. Log x equals 2.3. Log x equals 2.3. I don't have anything. Say it again. Yes, it's ln x natural log. ln is this one. ln. Good. So we're asked to find x. I have to change it into an exponential equation. What do I write? Exactly. 10 raised to 2.3 is x. And yes, I have to approximate that. How much did we get for 10 raised to 2.3? How much?
199.
Good. Awesome. Let's look at 43. Natural log x equals negative 2.3. Natural log x